So when I prefaced the buffer video before this, I said that a buffer is when you have a weak acid and its conjugate base. That's sort of misleading in that it suggests that you can't have a base and it's a weak base and it's conjugate acid, and you can, and that's also the same as a buffer. And so you might not have seen this before, but we can think about bases from, or we can think about buffers either from the acid or the base perspective. And so I just want to walk you through really quickly what that might look like. So, at the beginning here in sort of highlighting, we've got just a weak base, and it reacts with water via its Kb, the equilibrium base coefficient here. That's going to make BH plus, the protonated version of the base, and generate some OH minus. That's really the origin of the base itself. And so we can write up an equilibrium expression and set the concentration of the products over the concentration of the reactants to Kb, right? So no different than what we've ever done before, but we can derive a Henderson-Hasselbach equation that represents this from the base perspective. So same exact process. I'm not walking you through it step by step just to save time here, but we have log Kb and then log of the other side, the concentrations. Exact same process that I did. Take the log, separate the log, switch the sides so we get the negatives, and that gives us POH and PKB. And so what we get in green at the bottom, and you can just pause this and follow it if you want to work through this, but it's literally the exact same thing, is a Henderson-Hasselbach equation, but it's from the perspective of POH and PKB, and in this case we have the protonated form of the base over the non-protonated form of the base. This is just as useful as an expression, and you can use this. And so if you're given a base and you're talking about a buffer, or if you're in the middle of a titration, but maybe you're titrating a base with an acid, this can be a really helpful expression to use, especially if you're given PKBs instead of pKa's. The issue here, at least from a practical perspective, is that you may feel compelled to use this expression but forget that this is POH. And you'll get a value and it won't make sense because you'll be thinking you're computing pH. So you got to remember, if you're employing the PKB in a Henderson-Hasselbach expression, then what you're yielding out of that is the POH. That doesn't mean we can't think about a base from the normal in Henderson-Hasselbach, which you may have done sort of just unconsciously, but in that case what you're really thinking about is not the base itself and the reaction of base with water. You're thinking about the protonated form of the base, the BH plus, as it dissociates in water to form the original base and hydrogen ion. In that case, this is an acid, right? And so that is going to dissociate to some extent based on the Ka of the acid form, the protonated form. That's where things get confusing, because you have to make sure, if you're using Ka's and Kb's, you understand what those Ka's and Kb's are with respect to. So of course a Ka is only going to be associated with the acid version, and there's no acid version of the original base, so what that's referring to is actually the protonated form of the base. But it's not the reverse of this reaction, because remember, that would just be 1 over Kb. That's the base, the protonated form of the base reacting with pure hydroxide. What you're talking about with Ka would be the protonated form of the base just simply reacting with water and dissociating, in which case we would write this up as Ka equals concentration base, concentration hydrogen ion over concentration of the protonated form of the base. We would log both sides of this, and what we'd end up with is pH equal to pKa plus log, and then we would have base over the protonated form of the base, which is the exact same expression as what we had derived before in the previous video, pH equal to pKa plus log. In that case we use this A minus over the HA. Either way, they're exactly the same, right? It's base over protonated form, or it's conjugate base over the weak acid, but these are literally the same expression. So you can use either to solve these things. In certain cases, one is more convenient than the other. I just want to make really clear that Ka is associated with the protonated form of something, Kb is associated with the non-protonated form of something. And since we're dealing with weak acids and conjugate bases, it gets a little confusing when you're talking about weak bases and its conjugate acids, but really the expressions are the same.